Right, this is a resistant band. At the moment, it's in its original length. I'm not extending it, so there's zero tension. Right? So the more I stretch it, the more the extension, the more tension there is within the resistant band. So at the moment, that's the original. So if I increase it to double the length, there's quite a bit of tension there. So if I increase it even more, that's roughly 3 times its original length, and there's a lot of tension there. The more extension there is, the more resistance you'll have within the resistant band. Right, let's just pretend this is our resistant band that we just saw. Its original length, when it's not extended, is 100 centimeters, roughly 100 centimeters. So there's no tension. So if I anchor it here, and it's double the size from 100 to 200, which is roughly here, that's 200 centimeters. So what's happened is, it was at its original place, which is 100 centimeters, no extension, and then I extend it to 200 centimeters. So actually, extension is not 200. From here to here, it extended by 100 centimeters. So the extension is 100. And likewise, if I just take it further, and then now it's 3 times its size, 3 times its original size. So here, it's 300 centimeters. So the extension from here all the way to here is actually 200 centimeters. And that's what you saw in the video. Right, there is a connection between tension and extension. Tension is measured in newtons, it's a type of force, and extension I'm using centimeters for now. So the statement, tension is directly proportional to the extension of the resistant band. So tension is related to the extension, and it's written like this, using this symbol here. Tension is directly proportional to extension. So in other words, as extension increases, tension increases in proportional amounts, as we've just seen in the video. As I said, there's a connection between tension and extension. We found out from the experiment that when the extension is 100 centimeters, the tension is 250 newtons. So we can say tension is equal to, but you can't say tension is equal to extension. Clearly 100 is not equal to 250. Okay, if you put extension as 100 here and the tension as 250, 250 is not equal to 100. So what we introduce is K. K is a number which we need to find out. K is called the constant of proportionality. That's what we need to find out. So if we just substitute the numbers that we know already, tension is 250. K, don't know what it is, but I'm going to find out. And extension is 100. So 100 times something to give me 250. Well, you just do inverse operation, 250 divided by 100. So therefore K, 250 divided by 100 is 2.5. So the formula connecting tension with extension goes like this. Tension is equal to, what's the value of K we just found out? It's 2.5. And multiplied by extension. So now this thing here, this formula connects extension with tension. So for example, let's suppose extension happens to be 200 centimeters. what's the tension going to be? Well, if the extension is 200 centimeters, substitute the 200 in here. 200 times 2.5 is 500. It's what we saw in the video. And you can do the same for any of these numbers. So let's just put some random numbers here. 20, 40, 60, 80. So if you substitute the 20 into here, 2.5 times 20, 50. And so on. You can fill in all the other numbers using the formula. Well, here are the rest of the values filled in. All I have to do is substitute these numbers one at a time and then multiply by 2.5 in the formula. For direct proportionality to work, it has to start at 0 from the origin. So if you was to plot this on a graph, your straight line graph, it would be a straight line graph. It would start at the origin